So thank you all for staying and for attending this talk. My name is Andreas. I've been at the University of Toronto since 2000. Before that, I was at Northwestern University for a while, and before that, I was a student too. Today, I'm speaking in my capacity as a teacher over there. With my students also, we recently founded a company which tries to commercialize some of the technologies I'm going to be describing today as well. I'm also a scientific director of a research network we have up in Canada, which primary goal is machine learning acceleration at the hardware level. And finally, I'm affiliated with the Vector Institute. This is, what I'm doing overall. So I have to apologize a little bit. I didn't know what to expect out of this event, what kind of audience we'll give. I'll be a little bit self-centered in the beginning, give you a bit of background. The reason I'm doing that is to give you a perspective of why we're doing things the way we're doing it. Why we're approaching the problem with the way we're approaching it. So I was a teenager in the 80s, and my first interaction with computers was with this machine. My best friend actually was able to buy this, but his mom felt that he didn't do well in school, so they gave it to me, honestly. So I had the chance of playing with it for a couple of months. This was a very nice machine because the first thing you will do, the moment you plug it in, it will give you a prompt and you could program it in BASIC. So you had to learn programming to use it regardless. Now, as a teenager, somehow these things felt reasonable to me, like logical. Everything in the computer felt logical. That was my perception. I'm not saying that I understood everything perfectly. That's what I felt about computers. And I felt that software is easy. Right? Everybody can write software. And somehow, my 16-year-old felt that the most important thing in life is to build hardware. And I decided that this is the thing I wanted to do. That was as a teenager. And I'm lucky enough that through various events in my life, I got lucky enough to be able to keep doing that. However, now I'm not 16 anymore. And I kind of realized that the most important thing in life is not to build hardware. And actually, building hardware is not that far away from building a hammer. You're just building a tool. You give a person a hammer, unless they know what to do with it, right? It's just a hammer. There are people that will take a hammer and they will do nothing with it. There are people that will take a hammer and build like a statue, like Michelangelo or stuff like that. So, but I am not that person. I'm just building these kind of things. I do take solace, though, that it turns out that computers are very useful hammers. People use it for everything and anything. And one thing that people are using today is machine learning, which is, I had nothing to do with the development of machine learning. That's another lucky event in my life. I happened to be in Toronto, and then I happened back in 2009 to offer a course in CUDA programming. That was the first time that this course was being offered. Also, I got lucky that one of the students that was attending this course was Alex Krivetsky. And Alex is the person that developed AlexNet. As part of his class project, he did just a convolution layer. And I was lucky enough to have Hinton come into my office and ask me, what are these GPU things? What can you do with them? I tried to entice him, by the way, would you like to work with us to do some specialized hardware for this stuff that you guys are developing at the time? And of course, he wasn't interested because they had much better things to do. I had nothing to do with all this kind of stuff. I barely understood what they were doing at the time. But because I knew computer architecture and I knew that, like everybody else in the field, knew that the games of general purpose computing giving you 2x the performance every year, they're over, and we had to build specialized machines. This drew my attention, and I started trying to educate myself and learn what it is. So long story short, for the past, I would say close to 6 years, pretty much 100% of our time in my research group back in Toronto has been on trying to develop techniques for machine learning acceleration. Okay, and the goal for us has been always, but it is the goal of a computer architect, to build better machines that can compute more things faster with less energy so that people can use it to innovate. That's how the computing industry has come about. That's the role of hardware. People give you more capable machines. People that build software use them to do more interesting things with them. Now, some basic about computing, believe it or not, even if you take the most simple computer out there, and if you take the most powerful one, they really do just two things. They move information around, or they just compute things. They can manipulate information, transform it into something else. So if you want to build a better machine, you will need to find ways of doing these things better. So one application, again, just to make things concrete now, is machine learning. I'm going to primarily focus on classification tasks because they're easy to explain, but the stuff I'm going to describe does not apply only to those. So let's say, let's take your typical convolutional neural network. You give it an image, it passes through a bunch of compute blocks, and at the end you get some indication of what you may be looking at with some confidence, right? Now, long story short, regardless how you take this, at the end it boils down to a lot of these kind of operations. It's really very simple from the machine perspective. You have to do a lot of multiplications and accumulations. That's what you got to do. So the question for an architect becomes, how can I build machines that will allow me to do as many of those per unit of time with as little energy as possible? Okay. So I'm given this task. Right? And now here, and I know this has a lot of parallelism. When I say I'm given this task, what you get as a computer, if you were a machine, you will get a lot of these calculations you have to calculate. Now here we are back in my desk with my students thinking about 6 years ago, what should we work on so we remain relevant? And I'm thinking the following, I'm an academic, I don't work for a company. If I was working for a company, there's an obvious first thing I should do. I'm not saying it's easy what the solution is, I'm just saying there are obvious things you got to optimize first. There's a lot of parallelism there, so you're going to build a machine that has a lot of multiply accumulate units. First thing you do. That's why GPUs are very good at this. Second is to keep these units busy. I mean, it's easy to build a lot of compute units. You need to feed them with a lot of data. So I'm going to work also the memory system. And by the way, since the 50s and 60s, there is a lot of optimization techniques for blocking computation, that is taking subsets of those and trying to transfer them on your on-chip memory hierarchy. So you take data reuse, and I'm going to work on that. And we're thinking, these are the things, if I was working for NVIDIA or Intel, whatever, I will do tomorrow. I'm not saying I know what the solution will be to those, but these are the things they will work on, because these are the first things you should do to optimize these algorithms. If I do this as an academic, I'll get 2-3 papers out of this, good for me, but it's going to be completely irrelevant, because there's no way I will compete with 5 students that stay there for 2-3 years in the beginning of their career, and I will come up with something that's going to revolutionize the world. NVIDIA, with their thousands of engineers, are going to do much better than me. So, all the work we've done prior to this was on general purpose computing. And if you follow the history of general purpose computing processor design, you'll see that a lot of the stuff that actually processors do today that make them operate much faster and do things much faster for you, they rely on program behavior. That is, there are techniques that say these programs that are not random objects. They don't do random things. They do things in a particular way. It's like a person that wakes up in the morning and says, I want to have my coffee black. There's another person that wakes up and says, I want my coffee with 2 sugars. That's how programs behave. They tend to like specific behaviors. They tend to like specific things. That's why if you look at processors today, they tend to have caches. They tend to have branch predictions. They have to have many other optimization techniques. If I have $1 million to give you, and I said, write an algorithm that will show that caches are ineffective, you're going to get $1 million in a couple of seconds. It's very easy to write programs that will defeat these mechanisms. The reality is, though, that most programs actually like this kind of stuff. So we're looking at these computations. We're saying the following. You ask us to do a lot of multiply accumulates, transfer a lot of data, and do these operations. A key trick in computer architecture is the following. Do not do as you're taught. This is what the programmer wants to do. But it's not that exactly. This is a way of getting to an outcome, to a result. This is, the programmer says to you, if you follow this computation, you're going to calculate a bunch of values, and these values are the ones I care. This is one way of doing that. So our goal here is to do the same, to calculate the same output, however, to do it with less work without asking you to tell us how to do that. So long story short, you give me this blueprint of a computation. I want to find some automagical way, whatever that is, so I can take that computation and suddenly convert it to something like this and still give you the answer you want. Furthermore, even for the stuff that remains, the few computations that are left, I want to make them less expensive, some of them, not all of them. And the question is, what is that automagic way? It sounds like magic. No, it's not. And this is stuff that people have been doing with general purpose processors for ages. The question here is the following. The domain we're working on, or the ecosystem, is there's a programmer that sits down and devises all these models, neural networks, whatever. This goes through some kind of a software stack, like a compiler, maybe a runtime system, and then hardware. What I've learned in the few years I've been working in this area is that this is the hard part. That is, you want to allow this person to focus on doing their task without asking them to optimize for your hardware. Many times I've seen people come out and say, yeah, I give you this hardware. If you sit down and you optimize for my hardware, you're going to get 10x the performance. It's extremely unlikely that people will do that. Why? Because this is the hard task. You're going to spend most of your time here, and the last thing you want to do is you want to fiddle with bits or registers or stuff like that so you get the performance. So the question is, how can we somehow then build a system here that will take whatever you came up with and optimize it on the fly without you knowing. So this is the type of stuff we do. We don't assume anything about the evolution of the systems out there. We look at some fundamental operations and we're trying to find ways of either eliminating some of them or making it less costly. Just to make it more specific, let me give you one example. In modern systems, the following applies. You have some silicon chip that has a lot of compute cores with some on-chip memory, and then, because this is limited by the technology, right, it's a few hundreds of tens of megabytes today maybe, you have to go off-chip to get the rest of your data. This thing is very expensive. It's actually 100 times more expensive to go off-chip than to access something on-chip in terms of energy, and in today's technology, energy dictates performance because of thermal factors. So let's go back to our computation. You told me I want to do a gazillion of multiply accumulates. At any given point in time, I will go to memory and I will transfer some data. Right? Let's say I want to do, 8 multiply accumulates this moment. I want to transfer data for that. So I have to transfer some amount of data. So this has to be transferred from here. What do people do today? What's the conventional approach to computing? I don't know if you follow that, but it used to be computers were 8 bits, then they became 16 bits, 32 bits, 64 bits. What does that mean? It means that people choose a data type that they can conveniently support in their circuit level, and then programmers just use that data type. Today, this may be 8 bits or 16 bits for neural networks, right? That's what people do. They say, pick a data type, whatever you want, and represent all your values using that data type. Okay. Here's the thing, however. This ignores the realities of the actual values you're transferring. The realities, and this is a mock diagram, it's not an actual data from any neural network, but let's look at the activations, for example. This applies to the weights. And ignore that, but let's look at this. This is supposed to be 0. This is supposed to be the maximum value for your network. The distribution of values for pretty much everything we looked at looks something like that. That's how the distribution looks like. What this is supposed to depict is the following. Most values tend to be small in magnitude. They're close to 0. There are some values that are high in magnitude. These are the loud ones. These are the features you're discovering. These are important values, but there are few. Some people even quantize that. Let's say you started with a 16-bit network, you quantize it to 8 bits. What you've done, you condense this distribution, but again, the bulk of the values are here, and few are high. When you pick a container, say 8 bits or 16 bits, and you say, I'm going to use that to represent every single value with that, what you're doing is you're catering to the very loud voices in the room. Right? In a room, you may have 1,000 people. There's one person that's yelling, and you're saying, I'm going to devote all my attention to you just because there's one of you. There's something better you can do, and I hope you can see that. What you can do is the following. Let's say, again, I have a bunch of values I need to transfer, and I'm going to show you 2 of them here. For this particular packet of values that I'm transferring right now from memory, you can see that the maximum number of bits you needs to accommodate, for example, sorry, this diagram is a little bit off, but it should have been at 1 up here. So what I can do now is I can say, for this group and this group only, do not use 8 bits, use 6 bits. For another group, use 4 bits. For another group, 2 bits. Rarely I will get a value that will require all 8 bits. And now I apologize for these wonderful graphics here. This is copy-paste from one of our papers. And what I'm trying to show here is something that's kind of interesting. This is a fairly modern image classification network, ResNet 50. And these numbers here are basically the effective number of bits that we transfer per value for every layer. So there's a lot of numbers here because this network has about 50 layers to start with. What I want to point out is, first of all, if you look at these numbers, they're fractional. Why? Because when we transfer data, we say for every group we get from memory, say of 16 values, I'm going to use a different number of bits, and these bits are going to be dictated by what the actual value content, not what you chose to be the maximum precision for the layer. Your network might be 8 bits or 16 bits in this case. However, anytime you go to memory, you say, for these values that I'm storing right now, that I'm transferring, how many bits do I need? Long story short, you can see in some cases you have extreme cases like this. The average number of bits is below 2. Why? Because the distribution applies. This does not mean that all values use 2 bits. This means that most values tend to use this number of bits. Long story short, you do this kind of thing, and what we found is for most neural networks out there that are image classification, we can trim down your traffic to about 1/4. That's what it is. Of course, it varies per network and per layer, whatever, but that's the beauty of it. You rely on the properties of your values, not on on the worst case scenario. The nice thing about this is that this mechanism is completely transparent to your programmer. It's there, it works if your network has the properties. If it doesn't, well, it just stores 8-bit values. That's what it is. If tomorrow somehow your network's changed value distribution, you just throw it out. Why? Because you never expose it to anybody in terms of a programmer's interface. Now, what I just described is a technique to reduce the number of bits you transfer to memory. We also have technologies that allow you to take the same property and reduce the number of computations you have to do. Those designs, I was having a discussion before, I would say there's a lot of stuff we've done over the past 6 years. I'm very proud of each single one of them. There are some things that I've considered to be, okay, maybe I will build this today. There are some things that I think are a little bit risky. So this is maybe on the risky category. The idea behind it is the following. Let's say I'm taking back to primary school now. This is how we learn to do multiplication. You take two numbers, you take a digit from one of them, you multiply with the upper number, you write the result here, so on and so forth, right? And now, because this is the binary system, of course, anytime you multiply with a 0, you're getting a nice 0, which at the end, if you add, it does nothing to your result. So there is hardware you can build that actually detects, either statically on the fly, prefixes or suffixes that are all zeros, and basically only computes the middle part. That's what it is. So what I couple with the previous technique, we can actually make your machine go about 3 times faster than before, just because the values tend to be this way. Okay. Now, this is work that we've done maybe about 2 years ago. I will just take you back now to give you an overview of other stuff we've done. This is fairly standard these days. A lot of people are going after this. This is work that we've done back in 2016. The first observation we made for this kind of networks that often enough, a lot of the values happen to be zeros. And the part we worked on first was activations. These are runtime values, and a lot of them happen to be zeros. There is a reason why this happens in neural networks. This is the features you're looking for. So most of the time, a feature is not there where you're looking for it. Another thing we found at the time is the following, that there is a lot of tolerance in these algorithms. You can profile them actually, and you can find thresholds, that is, which is the new 0. That is, you can find values that are very close to 0 but not exactly 0. You can also practically treat them as 0. First thing, so if you do this kind of thing, sorry for the sound, you can get rid of about 50% in principle of your computation. That's what you get out of this. The interesting part is how do you design hardware to take advantage of that? And again, I'll be happy to tell you how we do that. I don't think there's enough time to reasonably do that in the time I have allotted today. So that was the first generation hardware we built. Next generation, I explained already that we can squeeze values from both left and right, get the result, get rid of this. This is bit serial hardware. This is back to the old days. Bit serial hardware, usually you use it to do low cost implementations. We actually use it for high performance implementations here. And if you do this kind of thing, depending on the network, you can get rid of about half to 75% of your work, depending on the network you have over there. And the latest thing with design we have is one that even gets rid of the middle zeros over here. This is I'm very proud of this design. It's very weird when you look at it. I'm not quite sure I will build it tomorrow, but it's kind of an interesting design to have out there. We have this for integers, and we also have a design for floating point as well. And we're looking at that for training, because it turns out that for training, there's a lot of 0 bits. Most of the stuff we've done is inference. And believe it or not, in some cases, particularly AlexNet, you can get rid of 99% of the work doing this. Every night, every time I say this result, I cringe. I'm saying this cannot be right. But I had several people in my group go and double check it 10 times to say this is true. Every time I say it, I don't believe it. But that's true for AlexNet. Most recent networks, they're not 99%. Okay. Another thing I want to point out, this is once you have this kind of hardware that can get rid of 0 bits and take advantage of value magnitudes, there is other stuff you can do. So a lot of the work we've done is for image classification networks. However, guess what? Machine learning is taking over the world and everybody's using it. There's another branch where machine learning has taken over, and this is computational photography. Right. Turns out computational photography for decades was dominated by analytical methods. People analyze the problems geometrically with statistics, and then they came up with closed formulas that say what you should do. Then somebody came up with machine learning, and guess what's going on in that field? They're just applying machine learning like crazy. what is somewhat different here is, at least for the networks we saw, is that they're fully convolutional. There are no fully connected layers. They do per pixel prediction, so they're essentially functions of every pixel here is a complex function of the input, but not necessarily of a small area. It can be a big area. And furthermore, these scale with resolution. Image classification, well, you give me a specific resolution and you train your network for that resolution. These guys, you want to do small images, you can do small images. You want to do 4K, you want to do 12 megapixel, 40 megapixel, same network works. Okay. Now, because this is a specific application domain, again, we'll look at the value properties. I don't think it will surprise you to tell you that images have spatial correlation in the values. What I'm trying to say is that if you look at images, look at this area. This is all pretty much red. Right? So pixels that are adjacent happen to have very similar values, if not identical. Guess what? Once you have hardware that benefits from the magnitude of the values, the smaller the value is, there's tricks you can play. One trick you can play here is you can take the same hardware and make it calculate deltas as opposed to raw values. And if you do this kind of thing, again, you get another 2x on top of that. Final thing I want to talk about, if I have time, is something that deals with pruning and sparsity. Pruning is a standard technique that many people try to use today to reduce the amount of work. Pruning amounts to taking weights and converting them to zeros during training or post-training. That's the idea here. So let's take a network. This is supposed to be an array of weights, an array of activations, and you have an array of physical multipliers. Once you have a dense network that is pretty much all values are non-zero, it's very easy to allocate things in physical space in your memories and your multipliers so that the right weight meets with the right activation at the right point in time. Time goes like this here and time goes like that here. It's very easy if you consider your network a dense network. All values matter. If, however, you have a sparse network, and this mock diagram now is supposed to represent values that are zeros with gray boxes, well, in order to get performance out of that, you have to somehow condense this and move values ahead in time. So you have to make this magenta guy appear earlier in time. And sometimes if you want to keep all your multipliers busy, you have to also move them in space, move them sideways. So you have to do this ahead motions and sideways motions. This does not play well with hardware today. GPUs cannot do that well because they're not designed for this kind of stuff, right? So you want to do this kind of thing, somehow do this. For weights, it's easy to do because you know the weights in advance, so you can pre-schedule things in memory and lay them serially. However, this means now you have to do the equivalent motions for the activations, and unfortunately you have to do this at runtime. Long story short, all solutions I've seen out there, they use expensive hardware to do that. They put a crossbar here, and crossbar is a very simple circuit, but it's ridiculously expensive hardware in terms of energy and area, so that you can allow arbitrary motions of the weights to be planned ahead. And then in runtime, you go and you grab the activation from all over the place. Trust me when I say this is expensive. That's the problem with this. So what we have here is the following. You have high cost and high latency, and it's the classical effort versus reward. People design for maximum potential benefit. However, to do that, they use maximum effort hardware as well. Well, there is a classical thing in life that is, you probably put a little bit of effort, you get most of the benefit. So have an alternate design, which does not allow you to do arbitrary motions. It's more like a game of chess. It says you can do certain kind of motions. The weight cannot go anywhere you want. It can go only to 8 places. Again, I understand I'm not giving you enough information to appreciate what's really been done. All you need to know for the time being is that for every weight, there's only a limited number of spaces you can move to. And then you have a nice scheduler, which is equivalent to a chess player, that makes the right moves. Long story short, with a lot less effort, we get most of the reward. And we end up with hardware that's a lot less costly. And we have some other tricks on top of ourselves at the end, we end up with a lot better performance because for the other side, we take a different benefit. Anyway, our hardware looks like this, roughly. It still has something that looks like multipliers underneath, and instead of a big crossbar, it has very small multiplexers with only a few choices. But because there is a lot of options, even though they're limited, you pretty much cover everything without requiring people to sparsify, prune your network in any particular way. This is one of the techniques I will put in the category. I will be that tomorrow. That's the kind of. This is completely value agnostic in what sense? It works with fixed point, it works with floating point, it works with anything you want. Okay, so long story short, our goal as a group is to say we don't know how software is going to evolve. We don't want to bother the programmer by saying optimize for my hardware. We want to come up with identify properties in the programs we are running and build hardware that take advantage of those without exposing to the software programmer necessarily. However, I would like to point out that a lot of techniques we have out there will reward you if you put some additional effort. Once you have hardware that takes advantage of magnitude, if you quantize something to 4 bits, well, I will give you something for it. And the most important thing is I will give you something for the 4-bit network without requiring that everything you do is done in 4 bits. Some of the networks can still run in 8 bits, I will still run them. For the 4 bits, I will give you something more. Now, last thing I want to point out is that this is an area that somehow I felt is going to be significant. Again, matter of luck back in a few years back. This is a 5-year effort. We managed to convince the Canadian government that this is worth investing. So we have managed to put together a research network up in Canada whose primary goal is hardware acceleration for machine learning. We do have some industrial partners. We'll be happy to have more. They have to be based in Canada, have operations over there. This is a research network of 19 PIs across several institutions in Canada and several companies up there, major players in the field. We are organized into 3 themes. The top theme is machine learning. The bottom thing is hardware, and that's the bulk of the work. And then some system software. This is a limited by US standards funding program. It's big by Canadian standards. We have a board of directors and all this kind of stuff. But if I tell you the amount, you'll laugh at me, because you probably get 2 students in a top US university with this kind of money. We have 19 PIs. This is my marketing slide for the network. So our crown jewel is, of course, the people that do machine learning. So we have some people that you may well know about this. So Joshua Benzo is one of them. Raquel Artisan, which is in Uber Labs, is another one. Sanya Finder, which now leads an NVIDIA lab in Toronto, is another one. And Chris Paul at Montreal Polytechnic is another one. He's with Element AI. Now, it's very hard to work with people that do machine learning these days if you don't know, because they get so much attention, so much money that they couldn't care less to talk to you. I can tell you for a fact that Joshua, for what's worth, is one of the people that cares the most about this kind of stuff, because I think I don't want to put words in his mouth, but that's what I understand. I think he understands that machine learning has to live in a physical environment. The hardware has a big role to play with it. Okay, and there's a bunch of other people. Okay, and I think I will stop here. What I wanted to mention is that a lot of the stuff we've done is in the domain of academia. However, with my students, we have recently formed a company and we're trying to commercialize some of these technologies. We do understand some of our strengths. We do understand a lot of our weaknesses as well. And we're looking to partner with somebody that can allow us to bring this to fruition as well. Okay? This doesn't mean we understand all our weaknesses. It just means that we are aware of certain ones. So thank you for your time. And if you have any questions, I'll be happy to take them.
Any questions?
Yes, sir.
So, one of the examples you mentioned that you went down to up to 99%.
Yes.
One of the examples you mentioned you went down to up to 99% savings. What was the cost in terms of accuracy loss?
All of these are numerically accurate. It's just that this number, okay, this is, by the way, for that slide, I'm sorry I didn't clarify that, this is the potential. The actual benefit you get from hardware is a lot less. So a good rule of thumb is you look at your potential. I would say if I'm in early stage of design, maybe I will get 50% of that if I'm lucky. The reason why it's so much is the following. That particular class of architectures keeps 0 bits. So, and for AlexNet, which was a 16-bit network and fairly loose, if you ask me, there are a lot of 0 bits there. There are more than 90 plus of those, actually 99. This doesn't mean there are 0 values. It means that the values are very sparse internally at the bit level. That's what it is. But this applies to earlier networks. More recent networks, you're looking between 75 and 85, but still very high. And interestingly enough, this also happens during training. For activations and what's the other one?
Any more questions?
The updates you do. Sorry, I forget the term now. During backpropagation, there are 2 things. You're changing activations and of weights, of course, but there's the derivatives. That's what sorry, I forget the terms. They have a lot of sparsity in the bit domain.
Any more questions? Okay, thank you very much, Andreas.
Thank you.
Okay, so next up we have Emir Arifi. Emir is the Director of Compliance Analytics and Technology at Discover Financial Services. And today his presentation is enabling next stage risk management capabilities